So let's now do an example on total internal reflection to see how that business works in practice. So here's a question. I'm going to explain the question to you. Then let it also be a thinker question. Maybe pause the video and try it yourself. See how far you can get before looking at my solution. So the description is that light is incident normally upon the long face of a symmetric prism. What's the range of values of alpha that will permit total reflection from both rear surfaces of the glass of a refractive index n 1.55. So what's happening is you have this prism over here. So it's a three-dimensional object. This is basically a cross section, a cut of it, and then the ray comes in here. And does it say it comes in? It comes in normally. Okay. So this is 90 degrees. So there's a light ray coming in here. Then it's going to go through, it's going to get transmitted and refracted and also reflected. If this angle is blunt enough, it's going to get totally internally reflected. So at this surface over here, as long as if you make the surface a point like that, it's more likely to get totally internally reflected. If this surface over here is like facing it, so this ray is close to 0 degree incidence, very close to the normal, it's more likely to go through and get refracted. So the point is this angle alpha needs to be such that this surface over here perform total internal reflection. Now after being reflected, so you have this angle of the prism at the top. So this is the angle of the prism. If you make this angle big, then it's not going to get reflected here. So the smaller this angle is, the more likely you'll have a total internal reflection on this side. However, you want this ray to, after it's reflected, to reflect off of this surface also with a total internal reflection. For that, if this surface is facing it like that, it's not going to get totally internally reflected. You want this to be blunt like that. So for this surface, an acute angle, a small angle over here, is more likely for this to succeed. For this one over here, the bigger the alpha is, the more likely it is to get totally internally reflected. So the point is, alpha will have a range. If it's too small, this will work, this won't work. If it's too big, this will work, but this won't work. So for both of them to work, there's like a range of alpha. And that's the question. You're trying to find the minimum value of alpha and the maximum value of alpha such that you have TIR both here and here. And so that's the question. So this is alpha. So you'll be using, so each of these angles over here, let me go ahead and maybe label some of these angles. So this is this angle here. Let's call this theta 1. This angle here will also be theta 1, just because it's a reflected angle. Then this comes over here. It has an angle of incidence of theta 2. It's going to get reflected also with theta 2. And then this is alpha. So you'll be using the rule of triangles, that all the three angles, they add up to 180 degrees. And so it's a symmetric prism that you have. So this angle here, if I call this beta, this angle will also be beta. So these angles are equal because it's symmetric. So now based on this, playing around with the angle, see if you can find the minimum and maximum value of alpha such that you have TIR over here and also TIR over here. So that's the question. So let me pause this and let you work this thing out. So let's make this a little thinker question. So see how far you can get with this, and then I'll go ahead and solve it. Okay, so let's begin by labeling some more angles on here. So this thing, let me call this thing gamma. Let's call this thing over here delta. You know, label the angle. Then just as a reminder, this line over here, this is a normal. Normal. And this line over here, this too is a normal. That's a 90 degree. Now let's see how these angles work out. So starting with this beta over here, in this triangle, this beta plus the alpha, they should add to 180 degrees. So you have the following condition. You have a beta plus alpha, this is equal to 180 degrees. So now you have an equation for this beta. So this beta will equal 180 minus alpha over 2. Okay, and let's call this equation 1. Next, let's find this theta 1 in terms of the other angle. So first of all, these two angles are equal. You have a reflection, so therefore these two angles will also be equal. So this is also a gamma over here. So if you look at theta 1, this is 90 degrees. So theta 1 plus gamma, that adds to 90 degrees. So you can express theta 1 in terms of the gamma. So you now have, let me move this thing up a little bit. There you go. Okay, so you now have theta 1 plus gamma. This is equal to 90 degrees because of the normal over here. So therefore, theta 1, this is equal to 90 minus gamma. Okay. Now, if you look at this triangle over here, then beta plus gamma plus this 90 degrees, that again adds to 180 degrees. So therefore, gamma is 90 minus beta. So let me go ahead and label this equation over here. Let's call it equation 1. Okay. So the next thing is the gamma plus beta, that adds to 90 degrees because this is a 90 degree angle. Oh my goodness, it's out of the view. Okay, sorry. Okay, yeah. So looking at this little triangle over here, the three angles add to 180 degrees. So beta plus the gamma plus this 90 degree normal here, they add to 180 degrees. So gamma is 90 minus the beta. So put this in here. So when you put that in there, you now have a theta 1. Okay, theta 1, this equals 90 minus gamma, but gamma is 90 minus beta. So therefore, minus 90 minus beta. And so therefore, theta 1 is equal to beta. So you have this relationship between theta 1 and beta. Now, beta had a connection with alpha here as per equation 1. So let's substitute equation 1 into equation 2 next. So put equation 2 into equation 1. So you have a theta 1 is equal to beta, and that's equal to, I'm just copying equation 1 for the value of beta. This is 180 minus alpha, the whole thing over 2. Now the next thing is this theta 1. Let me get back to the figure over here. This theta 1, for it to totally internally reflect, it needs to be more than the critical angle, which is theta c. So let's solve for theta c, the critical angle. In the meanwhile, to make sure we don't lose track of this, let's give this number here. So this is equation 3. So next, let's find the critical angle theta c. So the law of refraction states that n1 sine theta 1, this is equal to n2 sine theta 2. So when this is equal to the critical angle, the angle on the other side, the refracted side, it ends up being 90 degrees. So as soon as the angle is more than theta c, this is more than 90 degrees, which it cannot refract to that angle, it ends up turning into a reflection. So this over here, the N2, this is the refractive index of the air. The light is going from the glass into the air. So this is equal to 1, is just air. And on this side over here, this is the glass is going from the glass into the air, or at least trying to. And this is equal to 1.55. This is the glass. So we want to solve for the critical angle theta c. So this theta c, this is equal to arc sine of n2 over n1. And so that's equal to the arc sine of 1 over 1.55. And when you crunch that out, you get 40.2 degrees. So this is the critical angle. So this is theta c. Let's call this equation 4. Okay. So now going back to equation 3, for there to be a total internal reflection, theta 1 needs to be more than the critical angle. So this whole thing here, the 180 minus alpha over 2, that needs to be more than 40.2. So let's write that condition down. So combining 3 and 4, you end up with the following inequality actually. You want 180 minus alpha over 2. This needs to be not just the critical angle, it needs to be more than the critical angle. So it needs to be more than 40.2. So now solving for alpha, notice that it's negative alpha. Let's move the alpha to this side over here, and let's move the 40.2 over here. So this ends up becoming negative. Now also multiply the whole equation by the 2. You have the 2 in the denominator, multiply everything by 2. So you then end up with bringing the alpha to this side. Okay. You'll have a 180 over 2, well, you multiplied by 2. So you'll have 180 minus 80.4. This is more than alpha. Reversing this, you have alpha is less than, bring alpha to the left side and bring this over here and bring this whole thing to the other side over there. This more than ends up becoming less than because you flip the whole equation. So you now have alpha is less than 180 minus 80.4. And this is equal to 99.6. So this is one condition, that alpha is less than 99.6. If alpha is more than this angle, that first total internal reflection will not occur. So let's label this thing proudly and give it a number. So this is equation number 5. So this is one of the results actually. Now we need to look at the second reflection at that other surface and apply similar conditions to it. So now let's take a look at that. Next, let's focus on this triangle over here, where you have the gamma, the delta, and the alpha. Once again, being a triangle, these three should add to 180 degrees. And so you have the following relationship: delta plus gamma plus alpha is equal to 180 degrees. So let me write this down. So you have a delta plus this gamma plus the alpha, that's equal to 180 degrees. But these delta, the delta and the gamma, they're related to theta 2 and theta 1. How? This is a normal over here. So theta 2 plus delta, that's equal to 90 degrees. Theta 1 plus gamma is equal to 90 degrees. So you can express gamma as 90 minus theta 1 and delta as 90 minus theta 2. So let's put that into this equation here. Replace the delta and the gamma in favor of theta 1 and theta 2. So doing that, so you have, as I just said, the delta, that's equal to 90 minus theta 2. So this is 90 minus theta 2. Then plus the gamma, that's the gamma's up here. That's equal to 90 minus theta 1. This is the gamma, that's the theta 1. So here you have plus 90 minus theta 1 plus alpha. This is equal to 180 degrees. Okay, so let's go ahead and label this equation. So the last equation I had was 5. So let's call this equation 6. Okay. So we want to solve this equation for theta 2 because that's related to the critical angle. Now theta 1 can be related back to alpha. How so? We had this previous equation, equation 3, here it is. Okay. So this equation 3, the theta 1 is 180 minus alpha over 2. So we can replace this theta 1 in this equation 6 with this whole thing. This way theta 1 is gone. You have an equation only with alpha and with theta 2. So this is equal to, based on equation 3, 180 over 2 is 90 and minus alpha over 2, minus alpha over 2. So we can put this in there. And furthermore, if you notice that you have a plus 90, a plus 90, and a plus 180 degrees here. So these 90s will add to 180 degrees, and they will cancel this 180 degrees here. So this ends up becoming just a 0 on the right hand side. Now let's rearrange this for theta 2 and alpha. So when you do that, you end up with a theta 2 is equal to 3/2 alpha minus 90 degrees. And rearrange this to, for alpha. So alpha will equal 90 plus theta 2 times 2/3. Now for that second total internal reflection, this needs to be more than the critical angle. So let's put that in there. As soon as you put this greater than condition here, this ends up changing to alpha. Instead of being equal, it needs to be more than 90 plus the critical angle, which was 40.2. We found this earlier. This thing times 2/3. So let's crunch this out, and you find this is equal to 86.7 degrees. So when you crunch this out, you get 86.7 degrees. Let me kind of just clean this up. So you have the condition that that angle alpha of the prism, it needs to be more than 86.7 degrees. Let's call it equation 7. And this equation 7, together, this is one of the conditions. Okay. We found that for the first reflection, alpha needs to be less than 99.6. For the second reflection, it needs to be more than 86.7. So that's your window of opportunity to get both of those total internal reflection. You have 86.7 needs to be less than alpha, because alpha is more. And furthermore, it needs to be less than 99.6. So this is your sort of range of alphas within which you get both of those total internal reflection. And that's the final answer. Sometimes books may state this as less than or equal to. Equal to is not correct. When the incident angle is equal to the critical angle, the ray is parallel to the surface. It is not reflected. It needs to be a little bit more than the actual angle needs to be a little bit more than the critical angle for that reflection to occur. So this is the correct final answer, not less than or equal to, less than or equal to. It should be less than and less than in both of these places.